You're still muted though, Yossef, so. Unmute yourself and we can all hear.
Yes, yes,
okay.
Sorry.
Great. That's good, thanks.
And here's, okay. Nice to meet you all. Thank you for waiting for my talk. I'm Yossef Zenati. I'm from Johns Hopkins. I'm part of TACAN, and I'm focusing on using Skynet, trying to understand the final elements, focusing on our process. And after yesterday, John's and Erica and the discussion talks, and from I will start or skip all the introduction, especially after a nice talk by Enrico and Ari. So I will skip to directly to the what I'm doing in Skynet. And briefly, I will discuss with you all the Skynet activities in this project. So as John told us yesterday, Skynet is a general proposed modular nuclear reaction network that keeps track of entropy and temperature changes due to the nuclear reaction. It's evolving, and in this work, the process nucleosynthesis in the merger ejecta is performed based on the Skynet developed by Lippand and Robert in 2017. It's a nice review about the code, and I will use the version involving almost 8,000 nuclides and more than 1.5 10 to 5 nuclear reaction. And Skynet includes all the equation of state we know from, I think, from teams, and NEC problems. Or also you can add self-heating and electrons screening, and all the nuclear reaction we know, especially the weak interaction beta decay. And here just a frame I took from Robert Rook, just showing all the R process and S process could produced by Skynet using also the NEC, where the temperature, I think here was 10 gigakelvin. And I'm going to focus on what actually how we implement the physics properties from the dynamical ejecta from Newton's thousand-class mergers, where they are following Lipnerd in 2017 and Radici 2016. First method is known as the flux method. Maybe people familiar with this name, where they have been taking 3 space parameters to characterize the expanding material that undergoes the R process nucleosynthesis and produced a kilonova, hopefully. The first is the initial electron fraction, the second is the entropy, and the third is the expansion time scale, where these 3 parameters allow us to systematically study the impact of different ejecta properties on the properties of the ejecta material relevant to this event, Newton's thousandth merger. And also following RE simulation, as Ari mentioned, we are using HARM 3D plus NOC based on the HARM 3D, adding all the neutrinos reaction or emissivity we know to understand how the temperature or the electron fraction evolved in long evolution. And once I took these 3 parameters, I can move to Skynet. These 3 parameters, the electron fraction and entropy and the expansion time scale, I can define in each cell in the 3D simulation, 2D simulation, and following this Skynet evolving these numbers, and I can calculate the final, or not merely the Skynet, the final elements. As you can see here, this is the early results we get from this flux method, or the first method we know. Where tau2 is here is like 50 milliseconds, and tau1 is 10 milliseconds, where the y is 0.01, and you can see we actually reach almost more than 300 atomic mass, all the elements. And here I just develop the grid with different entropy, trying to understand what we missed, or what to answer our process pattern, the second peak or the third peak, and maybe these results could lead to better understanding of what we need from the equation of state, the optical depth, and of course the neutrino emissivity. So, and the second method we following is the tracer particles, where our process network is calculated by the post-processing. Those obtained the trajectories of the ejecta, and of course the rest of the temperature density evolution is taken directly from the hydrodynamics, and we like following our recent simulation, also these tracer particles ready to move to the next step is the using this tracer particle in Skynet. And just recently we succeed to run one case in very low simulation, and I stuck with the temperature has fallen a Kelvin, and maybe that's give us a change, the changes we need to understand from the composition and what we need to follow all the network, almost 8,000 nuclear species, starting from proton to element with Z112, and that's lay between the valley, as I present in the first slides, the value of beta stability and the neutron drip line. And as Ari mentioned, we believe that in the long-term evolution, also there's place for the weak interaction. So we focus on the trying to understand the neutrinos transfer heating, where our process take place. This is all what we include in our simulation, and where the material ejected and dynamically from the region where the neutron stars merges, and from the accretion disk also that form after the merger. and the details of the R process abundances we will follow by the tracer particle and compare between the two methods, the flux method, just simplify, make the problem more basic or simplest. So we define the three space parameter, and the second one following the tracer particle, and the third point, we're trying to understand how the neutrinos could transfer temperature to where the R process take place. And here, this is our solution. Me and Julian and others focus on the long-term neutrinos could affect the R process or the YE, where the R process take place. So, of course, of our understanding of the detailed composition of the ejecta and how this material sensitivity with respect to the physics of neutrino is still incomplete, and we're trying to understand that from both method we have in our simulation. And here's just this luminosity versus radius, and this is the emissivity, all the reaction we include, trying to understand if there's place for more heating rates or a different heating rates than other studies. And I'm sorry for that I skipped all the introduction, but this is all what we have from in this step in the nucleosynthesis in Skynet in our simulation. Here's my summary, and I'm ready to take any question.
Thank you very much, Yossef.
Yeah.
I do see, I'd like to see if there are questions among the participants with hands up. I do see a question from Jonah fairly early on. He was asking, in the right panel late time, why is the gas not approximately symmetric about the equator? So this is kind of this is probably fairly early on in your talk.
I'm sorry?
Is that what you said? Unless it was referring to Ari's talk, but Ari did suggest a response in the chat. In the right panel. So I think you were showing, you were showing actual MHD.
Yeah, as I say, like following Ari simulation, and I'm doing the last step before the radiative transfer, the nucleosynthesis or the abundances from neutron star to star members.
Okay. Are there other questions? I don't see any here. I did have just a question about when you're doing your entropy survey, how many, and you sort of fairly dense set. I don't know how many entropy values you went through.
You mean in the first
yes.
method? In the first method, I develop a grid starting from a very low entropy to hundreds, like 200-300 in log. Like
okay,
this is the entropy. Yes,
so
and the dynamical time scale starting from 0 to 70 milliseconds. Right now, we will see what until where we can get from this full 3D simulation in high resolution.
Okay.
Yes.
Okay, thank you very much. We should probably move on. I think